All right, welcome to Next Gen Manufacturing. Today we're talking about something pretty wild, how the simple act of listening can tell us the true strength of the most advanced materials out there. Yeah, you heard that right. It's a technique that is totally changing how we build, well, everything, from supersonic jets to the next generation of electric cars.
So let's put ourselves in the shoes of an engineer for a second. You're building something incredible, maybe the next big thing in aerospace or a revolutionary new car. And you're using these amazing new materials, stuff that's lighter and stronger than anything we've had before. But here's the big question, the one that keeps you up at night. How do you know it's strong enough? How can you be 100% sure without, having to break it just to find out?
Well, that's the massive challenge we're diving into. And the answer, it's kind of amazing. It's totally invisible and it's all about sound. We're talking about a way to essentially see inside a material, not with our eyes, but with our ears, or, well, with something that can listen way better than we can. Okay, so let's get into it. Section 1, the Next Gen Material Challenge. To really get why this sound-based method is so important, we have to first understand the problem with these new materials. All right, so we're talking about things like carbon fiber composites. And let me tell you, this stuff is the backbone of modern engineering for a reason. It's ridiculously strong, but also super lightweight. But here's the catch. It's not like a simple chunk of steel, which is pretty much the same strength no matter how you look at it. No, with composites, their strength is complex, it's hidden, and it's woven right into their very structure. And that brings us to a really important idea. And that idea has a fancy name, anisotropy. But don't let the word scare you, it's a super simple concept. Just think about a piece of wood, right? It's really tough to break it along the grain, but if you try to split it with the grain, it's way, way easier. That's anisotropy. And these advanced composites, they work in pretty much the same way. For an engineer, figuring out these different directional strengths, well, it's not just a nice to have, it is absolutely critical for safety and performance. Which brings us to our next section, an elegant solution. Ultrasound. So the big problem is, how do you measure all these complex properties without destroying the very part you're trying to test? The answer, believe it or not, comes from a field we usually associate with doctors' offices. Yep, ultrasound. And using it here is a total game changer. We're talking less waste, faster development. It's a huge deal. And, this isn't some common everyday thing. As researcher Yvon Chevalier puts it, and a lot of this explainer is based on his work, the application of ultrasonic waves in the domain of stiffness and damping properties of composite materials is less well known. So what he's saying is, look, we all kind of know about medical ultrasounds, right? But using sound waves like this for manufacturing, it's a whole other level of sophisticated science. It's literally a way to learn a material's deepest secrets without leaving a scratch. So you're probably wondering, how does this actually work? Well, the process is surprisingly simple, at least in principle. First, you send a super high-frequency sound wave, way, way higher than we can hear, right into the material. As that wave travels, you measure two things. First, how fast is it going? Its velocity. That tells you all about the material's stiffness. Second, how much does that wave weaken or fade as it passes through? That's called attenuation, and it tells you about the material's ability to absorb energy, or what engineers call damping. And what's so cool is that from just those two little pieces of data, you can build a complete character profile of the material. Okay, so now that we know what we're measuring, let's talk about how we measure it. Turns out there are basically two main ways to listen in on these materials. So you've got the transmission method versus the echo method. Let's break it down. The transmission method is kind of like playing catch. You have one device, the emitter, that throws the sound wave, and another one, the receiver, on the other side of the material to catch it. This setup is awesome for figuring out how fast the wave traveled, which gives you the stiffness. Then you have the echo method. This one is more like sonar, or how a bat navigates. One single device sends out a pulse, it hits the back of the material, and it bounces back like an echo. This method is the absolute best way to measure how much energy got lost along the way, that damping property we talked about. So just to visualize that transmission setup, it's a straight shot. You've got the emitter on one side, the material in the middle, and the receiver on the other. It's a one-way street. And the key piece of info here is just how long that trip took. Simple as that. That travel time gives you stiffness. And for the echo setup, it's a little different. Here, one device does all the work. It's both the speaker and the microphone. It shouts out a wave, the wave travels through the material, bounces off the far side, and comes right back.
And by listening carefully to that returning echo to see how much weaker it is, engineers can nail down exactly how much energy the material absorbed. All right, next up, decoding the material's secrets. So we've collected all this data, wave speed, wave weakness, but what's the point? What do we do with it? This, my friends, is where the magic happens. This is where we turn that raw data into pure engineering gold. Yeah, this isn't about just sticking numbers in a spreadsheet. No way. This data gets plugged into some pretty complex physics equations, and what comes out the other side is a complete character profile of the material. It translates how sound behaves inside the material into the language engineers speak. Stiffness, damping, the whole shebang. It gives you a full 3D map of the material's true nature. And check this out. This is what it looks like with real data from a glass epoxy composite. When they sent a sound wave along the direction of the fibers, they measured a stiffness of 52.5 gigapascals. Pretty strong. But then they sent the same wave across the fibers, and look what happens. The stiffness just plummets all the way down to 21.4. This is it. You are literally seeing that anisotropy we talked about right here in the numbers. 2.45 times. Let that sink in. The material is nearly 2.5 times stiffer in one direction compared to the other. Now, if you're the person designing an airplane wing or race car frame with this stuff, that's not just some minor detail on a spec sheet. That is the most important thing you need to know. It's the key to using the material not just safely, but in the smartest, most efficient way possible. It's the difference between a design that works and a design that's truly optimized. Okay, let's bring this all home in our final section. The science of certainty. Because at the end of the day, all this complex science, all this data, it boils down to one incredibly important thing: certainty. It's about having the confidence to build with the materials of tomorrow. And really, that's the whole point, isn't it? This whole science of listening gives engineers the rock-solid confidence they need to do their jobs. When you can understand a material's inner strength without ever having to damage it, you can push the limits. You can design things that are safer, lighter, and more efficient than we ever thought possible. This is how real next-gen innovation gets done. So, to wrap this all up, what are the big things to take away from this? First, remember that these advanced materials are anisotropic. Their strength depends on the direction. Second, we can figure out that strength by listening with high-frequency ultrasound without breaking anything. Third, we do that by measuring two simple things: how fast a wave travels, which tells us stiffness, and how much it weakens, which tells us about damping. And finally, and most importantly, all of this science is what gives us the confidence to build the safe, high-performance technology of the future.
It kind of makes you think, doesn't it? We just saw how an invisible sound wave can reveal the hidden strength of a material. So it leaves you with a question: what other invisible forces, what other unheard sounds are all around us, shaping the world we're building every single day? Something to chew on. Thanks so much for tuning in.